Welcome back to Omni Eyes. Today we explore the incredible dragonfly, nature's ultimate master of high-speed visual processing and tracking. If you think a modern 60 frames per second camera is incredibly fast, you need to look closer at this insect. The dragonfly possesses the fastest biological image processing supercomputer ever discovered in the entire natural world, dominating the skies completely. Look closely at these massive compound eyes, containing up to 30,000 individual optical units called ommatidia, working in perfect harmony. Each tiny lens captures a fraction of the environment, combining everything into a massive mosaic of continuous, high-speed visual data. For human beings, a standard movie is just a seamless sequence of still images flashing by at 24 frames. However, if a dragonfly watched that exact same movie, it would merely see a series of agonizingly slow, disconnected photographs. Their biological frame rate is estimated to be at least 5 times higher than our own human visual perception capabilities. This extraordinary speed means that the physical world appears to move in extreme slow motion from the perspective of dragonflies. Because time seems stretched, they have ample opportunity to react to sudden environmental changes and fast-moving targets around them. When hunting, this frame rate advantage allows them to predict the exact flight trajectory of their prey with absolute precision. They do not simply chase a mosquito. They calculate its future location and intercept it perfectly in the open air. In the modern surveillance industry, we refer to this exact same concept as real-time motion tracking and predictive targeting. The dragonfly brain processes multiple vectors simultaneously, instantly determining the speed, direction, and distance of a tiny, erratic flying object. They are not just observing the present moment. They are effectively calculating and seeing the immediate future of that movement. If engineers want to build an ultimate security system that never misses a single moment, they must study this creature. Let us dive deeper into the evolutionary history of these fascinating predators, who have ruled the skies for millions of years. Long before dinosaurs walked the earth, massive ancestors of the dragonflies of today hunted through dense prehistoric forests with identical visual systems. Their ocular anatomy has remained largely unchanged simply because it achieved a level of evolutionary perfection very early in history. Imagine having a nearly 360-degree field of vision without ever needing to turn your head around. The massive spherical eyes wrap entirely around their head, leaving almost no blind spots for potential predators to exploit successfully. Only directly behind them is there a tiny sliver of space where their incredible visual coverage cannot completely reach out. This panoramic view is constantly feeding immense amounts of raw visual data directly into their highly specialized, hyperactive nervous system. Unlike human brains, which filter out excessive visual noise, the dragonfly processes everything simultaneously, with breathtaking speed and unyielding accuracy. They have specialized neurons dedicated solely to detecting the slightest motion against complex, highly textured backgrounds like forests or ponds. These target-detecting neurons fire rapidly the moment a small object moves, instantly overriding other sensory inputs to command action. It is a biological reflex so incredibly fast that the conscious thought process is entirely bypassed in favor of speed. Let us examine the mechanics of their interception strategy, a marvel of biological geometry and advanced physical mathematics in action. When a target is identified, the dragonfly locks its vision onto the prey, keeping the image centered on its retina. As the prey moves, the dragonfly adjusts its own flight path to maintain that perfect optical alignment until the strike. This parallel navigation technique guarantees a successful catch rate of over 95%, making them the most lethal hunters in nature. Compare this staggering success rate to a great white shark or a lion, which only succeed in about 20%. The secret lies entirely within those massive ommatidia, acting as an array of ultra-sensitive motion detectors scattered across space. Each ommatidium points in a slightly different direction, equipped with its own lens, crystalline cone, and light-sensitive visual cells. Together, they function like an immense wall of security monitors, each displaying a slightly different angle of the surrounding environment. Furthermore, dragonflies possess incredible color vision that far surpasses human capabilities, allowing them to see ultraviolet light and polarized light. Seeing polarized light helps them navigate by the sun and easily identify bodies of water reflecting light from the surface. Ultraviolet vision allows them to see hidden patterns on flowers and the wings of other insects invisible to our eyes. This multispectral perception, combined with ultra-fast processing, creates a highly detailed, vibrant, an incredibly dynamic view of reality. Now, let us shift our focus to how human engineers are actively attempting to replicate this biological masterpiece in technology. Traditional cameras capture full frames linearly, which requires massive amounts of processing power to analyze motion and track fast objects. Neuromorphic cameras, inspired directly by insect vision, operate differently by only recording changes in light intensity at individual pixel levels. This means the camera only transmits data when something actually moves, drastically reducing the computational load and increasing processing speed. Just like the dragonfly eye, these advanced sensors can track high-speed projectiles in real time without lag or blurring. Autonomous drones equipped with this biomimetic technology can navigate through dense forests at incredible speeds without crashing into unexpected obstacles. They can detect an incoming threat and alter their flight path in mere milliseconds, mimicking the evasive maneuvers of insects. The military and defense sectors are heavily investing in these dragonfly-inspired optical tracking systems for advanced missile interception protocols. Imagine a defense system that does not just track a target, but anticipates its evasive maneuvers with flawless mathematical precision. This is the true power of high-speed motion prediction, a skill perfected by nature over 300 million years. Beyond military applications, this technology is revolutionizing sports broadcasting, allowing cameras to follow fast-moving balls autonomously with perfect focus. Self-driving cars also benefit from these principles, using advanced visual arrays to predict pedestrian movements and prevent fatal accidents. The ability to process visual information faster than the speed of human thought is becoming the ultimate goal of robotics. Let us return to the pond, where our biological marvel is demonstrating these complex computational feats naturally in the wild. The dragonfly accelerates instantly, pulling forces that would easily cause a human fighter pilot to lose consciousness from the strain. It approaches the fly not from behind, but from below, remaining perfectly hidden within the blind spot of its prey. Its spiky legs extend forward like a basket, ready to snatch the unsuspecting victim out of the air with precision. The interception takes less than half a second, a brutal and efficient display of predictive tracking and unparalleled aerial agility. To capture this event on film, wildlife documentarians must use specialized high-speed cameras, shooting at thousands of frames per second. Only when the footage is slowed down drastically can we truly appreciate the complex aerodynamics and visual calculations taking place. It is a symphony of biology and physics, orchestrated entirely by a brain no larger than a tiny grain of rice. Yet this microscopic brain outperforms our most advanced silicon chips when it comes to energy efficiency and real-time processing. An artificial intelligence system attempting to replicate this hunt would require massive battery packs and heavy cooling systems to function. The structure of the ommatidia is also inspiring new designs for solar panels, maximizing light absorption from multiple different angles. Nature has already solved many of the complex engineering problems we face today. We simply need to observe and learn. The compound eye is a testament to the power of natural selection, refining a design until it reaches absolute perfection. Even their wings are integrated into their visual system, with special sensors providing feedback on air pressure and wind resistance. This creates a holistic sensory loop, where vision and flight mechanics are essentially one unified, incredibly fast biological software program. When a dragonfly loses an eye or suffers visual damage, its ability to hunt and survive is almost completely destroyed. Their entire existence is built around this supreme optical advantage, making them the undisputed masters of their microscopic aerial domain. Let us take a moment to appreciate the sheer beauty of their eyes, often glowing with vibrant, iridescent metallic colors. These colors are not just for show. They help filter specific wavelengths of light, enhancing contrast against the bright sky. Depending on the species, the top half of the eye might be optimized for looking up at the bright sunlight. Meanwhile, the bottom half is specifically tuned to look down into the darker, murky waters to spot emerging aquatic insects. This dual-zone visual processing is like having two entirely different camera systems seamlessly integrated into one single continuous feed. It allows them to monitor threats from birds above while simultaneously tracking potential meals swimming or flying closer to the ground. In the realm of artificial vision, achieving this kind of dynamic range without losing processing speed remains a massive challenge. As we continue to push the boundaries of machine learning, the principles of insect vision will become increasingly more important. We are moving away from brute force computing towards elegant, biomimetic solutions that process information smarter, faster, and much cheaper. The next generation of smart security cameras will not just record video, they will understand and predict motion instantly, autonomously. They will be able to differentiate between a falling leaf and a trespassing individual in a fraction of a second. All of these incredible technological advancements owe a massive debt to the humble dragonfly and its spectacular, multifaceted compound eyes. So the next time you see one of these creatures darting around a pond, remember, you are watching a supercomputer. You are witnessing a biological machine processing the world at a frame rate that makes our reality look like molasses. They live in a fast-forward dimension, navigating a world of complex trajectories and instant calculations invisible to human perception. Their evolutionary journey has given them the ultimate gift of foresight, the ability to see where things will eventually be. It is a profound reminder that human technology still has a very long way to go to catch up with nature. We proudly build machines that can process billions of calculations, yet struggle to swat a simple fly in midair. The dragonfly achieves this effortlessly, day after day, utilizing millions of years of refined, highly specialized biological coding and programming. As we map their neural pathways, we unlock the hidden secrets of high-speed motion tracking and advanced visual perception. Perhaps one day, our own artificial eyes will be able to see the world with the same breathtaking, unmatched clarity. Until then, we can only marvel at the intricate design of the ommatidia and the lightning-fast reflexes they provide. The study of biomimicry continues to bridge the gap between organic life and cutting-edge technological innovation in modern science. From the murky depths of prehistoric swamps to the sterile laboratories of modern robotics, the dragonfly has remained a marvel. They are the undisputed kings of the insect world, armed with vision that essentially allows them to predict the future. We have learned so much from their anatomy, transforming our understanding of optics, motion detection, and efficient neural data processing. The future of surveillance, autonomous navigation, and predictive targeting is inextricably linked to the biological secrets held within their eyes. Thank you for joining us on this deep dive into the fascinating world of high-speed biological image processing today. We hope you never look at these incredible, fast-flying insects the exact same way ever again in your life. This has been Omni Eyes, bringing you the wonders of vision. Stay curious, and we will see you next time, everyone.